Hello everyone, this is Akhilesh from Electronics and Instrumentation Department of RV College of Engineering, and here we are a group of 4 people consisting of Jensi, me, Ramakrishna and Shriya, guided by Professor Harsha, and we are here to give a short presentation on our technical seminar topic, that is Industrial Internet of Things for Industry 4.0, Architectural Vulnerabilities, Security and Application. Coming to the introduction, whenever we think about Industry 4.0, the first thing which comes to our mind is interconnection of various components like sensors, actuators, control systems, and other subsystems. But the normal IoT that we see around us, the usual IoT which is used for smart home automation and applications like that, the technologies which are used in these systems, it cannot be directly used in an industrial environment because an industrial environment is a little more critical and it require much more accuracy and speed as well. So the technologies which are used in a normal IoT system, they have to be modified a little so that their efficiency can be increased, so that they can be used in an industrial environment. So here is where industrial Internet of Things comes into the picture. So in this presentation, we will primarily be focusing on architecture, vulnerability, security, and applications of industrial IoT in Industry 4.0. So this is a normal flow of signal from a workstation to internet services. It is a generic block diagram of a normal industrial IoT system. Coming to the architecture. So architecture is basically how all the subsystems are connected in an industrial IoT system. So here we have a few of them. So the first one is wireless IoT based on IEEE 802.15.4 2015 TSCH access mode. So the traditional IEEE 802.15.4, which is based on ZigBee protocol, it is widely used in normal IoT systems, but it cannot directly be used in an industrial setup because it has relatively high power loss and interferes from other wireless sources. This is primarily because it uses CSMA for communication, for which the sensor always has to be active all the time, which leads to power loss. And also it uses a single channel system. So in a single channel system, it uses the same frequency, so there can be interference from other wireless sources which are using the same frequency. So in order to overcome these drawbacks, this protocol was modified to IEEE 802.15.4 2015 time slotted channel hopping access mode. So this particular protocol, it uses the advantages of both TDMA as well as FDMA. So the whole channel is divided into several slots in time, and they're sent in the form of slots, and each slot has its own frequency so that there's no interference as well. So in this way, the drawbacks of the normal IEEE 802.15.4 is rectified. So here is the normal flow of how the data is transmitted in this protocol. So first we have the physical layer, then the data link layer, then IPv6 adaptation, two layers of those, then the network layer, transportation layer, and finally the application layer. And towards the right are the protocols which are used in each of these layers. So the next architecture is the SDN architecture, that is self-adaptive software-defined networking architecture. So this architecture primarily focuses on separating the control layer from the infrastructure layer. So that is decoupling the control plane from the data plane. So this enables the network to intelligently and centrally control the entire system using software applications. So the controller which we use here, it's not in hardware form, it's completely in software form. And the infrastructure layer that we see here, sorry, the infrastructure layer that we see here is completely independent of any controlling. So the infrastructure primarily it just sends data from one point in the network to another based on the information it gets from the control layer. So it is a three-layered system, as we can see from the image towards the right. The first one is the infrastructure layer, which is basically the physical layer, which consists of all the wiring and network switches. And then is the control layer, which does all the controlling activity. And then comes the application layer. So these three layers, they are interconnected to each other through APIs. So the APIs which connect the control layer and the application layer are known as northbound APIs, and the ones which connect the control layer with the infrastructure layer are known as southbound APIs. So here is a more complex image which shows how the control layer is separated from the physical layer. So at the top we have business app, SDN app, and networking app, which come under the application layer. And in between we have the controller, which are in software form, so that the network, the as we can see, the control plane and data plane can be separated properly. The next one is layered data bus architecture. So this architecture consists of data buses at different layers of an industry that are interconnected to each other. As we can see on the right, we have four separate data buses in an entire industrial setup. The first one is the intersect data bus, the second is the site data bus, third is unit data bus, and primarily the machine data bus at the end. A data bus can be deployed within a smart machine to connect its internal sensors and actuators and analytics, that is the bottommost layer. At a higher smart system level, another data bus can be used for communication between the machines, that is at the system layer, that is the unit data bus. At a higher smart level system, that is at system of systems, another data bus can be used for communication between the machines. And at a system of systems level, different data bus can be connected together in a series of systems for coordinated control and monitoring and analysis. So the next architecture is using LoRaWAN based network. So LoRa stands for long range, and WAN of course stands for wide area network. So this requires end devices that consume extremely low powers in the order of 10 to 25 milliwatts. So this is the main advantage of this system. It has very low power consumption, and the network can also transmit and receive data at many frequencies between 150 megahertz and 1 gigahertz. So we have a very huge frequency band, which reduces the chances of interference as well. So towards the right, we have a general LoRaWAN based system. So we can see that the end devices are connected to the gateways in a star topology format. This in turn is connected to a network server through TCP/IP protocol, that is through either Ethernet or 3G or any other suitable format. And then this network server connects it to the application server, where all the cloud computing basically happens, and the data is again sent back to the end devices.
More and more IoT devices being deployed every day, it is expected that a billion of devices are to be connected on cloud services by the end of 2020. So it is highly important for us to understand the security of these systems. So first, we need to look at the private and public kind of networks that these belong to, and the kind of attacks or the vulnerabilities that these networks face. One such attack could be that this paper focuses on are the denial of service attacks and also unauthorized network access. That is the hacking or spoofing that is done by private individuals to leak sensitive information. Secondly, the sixth paper spoke about the commercial IoT devices that should be taken into account at the design stage itself so that there could be a unique branding for each device so that they can be secured at the device level. An up-to-date version of a current IoT cybersecurity is what is the aim of this section of the paper. And by doing the required literature survey, we are achieving that. Moving on, we have the problems related to cybersecurity in IoT systems in the seventh paper, which mainly discusses the physical and MAC layer communications and the vulnerabilities and the counteractions that can be taken place in this level in the OSI reference module. Next, we have from 8 to 13 papers which mainly deal with the vulnerabilities that are not in a practical zone, whereas it is more of a hypothetical data link failure or mo- more more at the connection end itself, wherein the data failure could occur due to the device damage or such hypothetical conditions, and necessary uh, counteractions were not provided in these papers. So this review paper here aims at uh, uh, providing the practical vulnerabilities of all the commercial IoT products as well as counteractions for the same. So here is a simple architecture of a smart lighting system, and we can understand that the router here can be having a lot of vulnerability with respect to the uh, devices that it is connected to, because we see that a computer and a smartphone are connected to the router. However, it can be also uh, said that more devices can be connected over this router by hacking, because this router is again connected to the internet. So there is a lot of vulnerability that is at this end, and the other end is essentially a gateway which just follows the commands from the router. So we tend to control the lights over here, which are currently here based on Zigbee protocol. So we follow it using using a smartphone app or a software on the computer to control the lights. However, these could be controlled by other devices which are not part of the network and which are gaining illegal access. So to curb these, we have requirements at every level. So first we have something called as the information level, which talks about the integrity, the confidentiality, the anonymity, and the privacy requirements. So these requirements are with respect to the security of any IoT system. So these papers are talking about these particular uh, requirements, that is the 16th and the 17th. Next is the access level. Access level provides the access control, authentication, and authorization. Here, what happens is the kind of passwords for security that are used, and who gets the access, and who gets to control, and all the admin roles are defined at this level. Next is the functional level. That is, what are the functions that the security can perform at various level of the organization. So these are the basic requirements of any IoT system. And further, we have the security attacks that could possibly exist at every layer if you consider an IoT architecture as covered before. So if you take at the edge layer, we have something known as the side channel attacks. So side channel attacks are very common these days, wherein they try to bug the hardware, they as in the hackers, with side channel leaks and such as power consumption, as you can see here, and electromagnetic emissions, and these kind of bugs that are introduced into the hardware through software scripts lead to edge layer side channel attacks. Next is the access or the middleware layer, wherein there is sniffing, that is known as eavesdropping, wherein we the hackers get unauthorized access to just stay on the network and listen to all the communication over the network. Next, we have the application layer, wherein they directly target the application level of the software that is running in the communication. Next is the functionality threats that could exist. That is like ignoring the functionality or reducing it, misusing it, or extending the functionality. All these come under the 18th paper as we have referred. So to summarize, here is a block diagram that can make us understand of all the attacks, IoT security attacks that could exist. So first we can talk about the physical attacks, which is like the node tampering or the device damage, or malicious code injection, or RF interference, or physical damage, as we have discussed. So these are all the physical attacks. Next, we talk about the software attacks, where we have scripts or phishing attacks, wherein they try to uh, bug the software alone, and with unnecessary scripts or extending functionality, and also viruses or spyware that can run on the networks, as well as denial of service attacks, wherein they burst a lot of inputs and the service cannot be accessed anymore. So that is the denial of service attack. And next we have the network attacks, wherein they try to get into the network and do the traffic analysis, as well as cloning and spoofing, which is really not a advisory or recommended thing. Next is the encryption attacks. Encryption attacks include the side channel attacks, as I explained before. Next includes the cryptanalysis attacks, wherein they try to break the cryptographic codes that are running to secure the system, and so on. So here are some security mechanisms for these IoT services. So there's something called as lightweight cryptography. These days, the hardware also has optimal code. So hence, this paper that we found was from the recent technology, which could have an encryption block, which is a very lightweight package and very highly efficient in security. And so far, there was no breakage of this cryptographic security, and with limited computation and communication and storage capacity, it stands out from the other cryptographic algorithms. Next is the random number generation, which is based on time intervals. So it generates a pseudo or random number of for different purposes, and also provides an authentication phase to avoid the replay attacks. That means every instant the random numbers keep generating, so there is more security because it is random, and it generates asymmetric keys to provide more security. And this is from another paper that that is from the latest security mechanisms. Next is the secure hardware. So there's something called as physically unclonable functions. So to improve the hardware security, the companies are now venturing into the security at the fabrication process of the chip itself, wherein they're provided with a unique signature at the device level, which improves the security to another level. Next is the intrusion detection systems. So these include traffic analyzers or antivirus softwares, or so many other uh, methods wherein it tries to indicate or monitor the network as a whole, and provide us information whenever an attack is taking place. And this also takes machine learning into account, wherein it can detect the intrusion process in a better way. So the intrusion detection is also done by the packets that are moving, and if there are any anomalies in the power consumption, as the power drawn is more when more number of devices are connected, and this allows to improve the security of the IoT services. Here are some popular IoT communication technologies like Zigbee, Bluetooth, and LoRa. LoRa is long range short form, and it is the latest technology for outdoor communication, and it is using RF, that is radio frequency. So Zigbee is a two-way wireless communication, and it is low cost and low power consumption, and it is mostly used because it has a link or a network key that is generated elsewhere, that is by the Zigbee Alliance Trusted Center itself, and then it is communicated back to the device, and hence it is widely used because of the security protocol that it follows. Also, it is always connected on a mesh network, so if you bring a new Zigbee device, it has to be configured to the new network, and that also improves the security, as no other Zigbee any Zigbee node that is bought in the market cannot be automatically connected because it breaks the security policy. Uh, Next, we talk about the Bluetooth low energy network. It has masters and slaves, and it is very secure in a way because it shares a unique pairing code between the master and the slave. And masters initiate the communication setup, and the slaves associate to them accordingly. And there is nothing that can go wrong in Bluetooth security. Next comes the LoRa. It follows a single hop chirp mechanism, and it uses radio frequency. So, however, people say that it can be easily tapped since radio frequency is just existent. But no, this is highly encoded radio frequency signals that it is sending, and It also exists in star topology, and it includes various end devices and gateways and network server which provide more security. Gateways are the ones that collect all the nodes information and pass it on to the network server. So this improves the security as a whole.
Industrial Internet of Things is an ever growing and rapidly increasing sector that accounts for most of the share of IoT spending in the global market. Industrialists and manufacturers in almost every sector have a tremendous opportunity to not only monitor but also automate many of the complex processes involved in manufacturing. For a long time, industries and plants have had sensors and systems to track progress, but now IoT takes a step further and provides intricacies even to the minute problems. Coming to the applications of IoT, smart robotics is one of the main applications which is no longer confined to conventional sectors like automation and manufacturing. As a technology, smart robotic is undergoing a massive change and is being deployed for a diverse range of applications across multiple industries like healthcare, retail, agriculture, logistics, and banking. And engineers and researchers are taking advantage of these developments to create intelligent robots to the future. Researchers from MIT have developed a robopicker which grasps and picks according to the manufacturer's instructions. A smart robot is an AI system that can learn from its environment and also experiences and build capabilities based on that knowledge. Many companies are developing intelligent robotic systems for IoT enabled factories, wherein smart robotic ensures smooth handling of tools and materials in the manufacturing line with precise accuracy and efficiency. Predefined specifications can also be set for maximum precision using intelligent robotic arms. Engineering team can access and analyze this data to take quick actions for product improvements or preventing an unexpected failure due to any machine fault. Robots can also be programmed to perform complex tasks with high end embedded sensors for real time analysis. These sensor networks are also connected to a secure cloud for monitoring and controlling, and there's been massive development in a robot picker which grasps and packs according to the manufacturer's instructions. There has been development in object agnostic grasping algorithm also, wherein the robot has to access a bin of robot random objects and also determine the best way to grip or suction onto an item amid the clutter without even having to know what the object is being picked. The next application is digital twin. So, digital twin in manufacturing is one such application which is widely being discussed these days. Along with the rise of new IT, the scope, degree, and functions of the cyber world of manufacturing and the integration with the physical world have been strengthened. Digital twin paves a cyber and physical integration as it serves as a bridge between the physical world and also the cyber world, providing the manufacturing enterprises with a new way to carry out smart production and precision management. Therefore, the digital twin is composed of three components: the physical entities in the physical world, the virtual models in the virtual world, and the connected data that ties the two worlds together. It reflects the two way dynamic mapping for physical objects and the virtual models and is nothing but just the virtualization of physical entities. The physical operations are judged, analyzed, predicted, and then the simulation and optimization of product design is being done, and then the physical process is being performed with optimal solution. In the process of interaction between the physical and the virtual world, the integration of data is an inevitable trend, and the simulation data is being fed back to the physical world to respond to the changes. Thus, the Smart Manufacturing and Digital Twin Workshop is proven to be very useful in the industry, wherein the proven product design is input to the smart workshop or the factory which is to be manufactured, and the input of the raw material to the output, that is the finished goods, the whole manufacturing process is being manufactured and managed and optimized through the digital twin. So, coming to another application wherein the Living Heart project is employed with the digital twin technology to model the cardiovascular system for research, treatment, clinical trials, and other scientific and commercial uses. The default model can be turned into a digital twin of a particular patient's heart with the help of their medical data. And this data, the heart model obtains unique characteristic of heart, that is the cardiac electricity, structure, blood flow of a specific patient, and other important data of the patient's heart. The multiscale heart twin also reconstructs the patient's cardiovascular system's behavior according to the current health status or condition, simulating various cardiac defects and cardiovascular diseases. Thus, digital twin plays an important role in industry. Now, coming to blockchain applications of IIoT, wherein supply chain or logistics is being considered. Blockchain is nothing but as an encrypted distributed database that records data, or in other words, it is a digital ledger of transactions, contracts that needs to be independently recorded. Supply chain or logistics with blockchain innovation, exchanges, and transactions are reported in a permanent decentralized ledger. Thus, these transactions are monitored transparently and securely and can reduce human slip ups and time delays and help to check the authenticity of the items by tracing their origin. Food traceability between 2013 and 2016, there was an outbreak of Listeria infection in several states of US due to the consumption of contaminated food products. By the time the source of contamination was being identified, a significant amount of time had already been passed, with more people being infected by the bacteria. And by the time the Food and Drug Administration realized the extent of infection, it was too late and the spread of the bacteria was too large. Thus, the recall was later expanded to include 300 products marketed under various brands and a tracking mechanism for the finished product from its source to the origin at various points in supply chain could have actually averted this incident, and blockchain can efficiently address the traceability issues in food supply chains. Due to the lack of mechanism for identifying and isolating such contaminated food products, incidents such as listeria discussed above can cost a lot to the food and the beverage industry. Thus, it is very important and an important sector in IIoT for the blockchain to be used. As you can see, a block diagram of the blockchain, where in the manufacturing house, the logistic information is being tracked, and then the manufacturing hub till the warehouse. From the warehouse, the product traceability information from the warehouse is sent to the local distributor, wherein the logistic information is tracked in the blockchain to the customer, and the customer empowers to provide anonymous feedback about the product upon receipt to the manufacturing house.
And the next application is an architecture for agent-based manufacturing system in the context of Industry 4.0. So cyber physical systems have always been a part of large-scale manufacturing, but in this application, it is based on a self-assisted network consisting of different agents that work together and ensure that the process is complete. The different agents are suggestion agent, conveying agent, and machining agent. Furthermore, the agent's interaction behavior is modeled into a structure of agent to reduce the complexity. Because the interaction among the agents is a distributed system and it is difficult to understand and predict what is happening. So, the experimental results show that the presented architecture can be easily deployed to build a smart manufacturing system that can improve adaptiveness to any changes that is happening at any moment of time. And the suggestion agent, and talking about various agents, that suggestion agent is the major agent which receives the order and monitors all the other agents working together, and ensures that the quality and the product is very well maintained. And then when we go to machining agent, they are involved in basically machining or completing the process of the manufacturing. And then when it comes to conveying agent, they ensure that they act as a gap or the transportation between the delivery and the source and the destination. This is a pictorial representation on how the various agents communicate between each other. And the next application is the IoT-based intelligent control and management system for motorcycle endurance test. Basically, IoT is a new generation intelligence system on the real-time network and embedded system. It contains a global internet with all other applications and capabilities in direct control with the physical world. So to and then this application basically works on different layers, and they are data acquisition layer, cognitive layer, network layer, and control layer. Basically, the data acquisition layer is where the data is acquired from the destination or the source, and the cognitive layer is where the data processing and interaction and various protocols are discussed, and network layer forms a connection between different layers to transport or communicate data, like using protocols like TCP/IP protocols. And then we have control layer, wherein it actually exchanges information with the external world. And the working procedure goes in this order primarily. First, the front end data collection is done, and then processes like analysis of any abnormal activities that is occurring, or any defects or any deviations are to be analyzed. And then we have feedback collection system, feedback transmission system, and collection. And then the cloud management system happens when while interacting with other servers. And then we have real-time perception of and automatic feedback state, wherein the collected feedback is real time is analyzed in real time. And then we have feedback analysis, wherein we figure out what are the errors caused and why the response from the feedback is occurred in particular order. So that is what comes under feedback analysis. And the next application is the Red Tag, a predictive maintenance framework for parcel delivery services. We receive a lot of parcels, and some of them are broken or dismantled. So to ensure that we can sort out the damaged ones or the improper ones, there's a thing called Red Tag, which is attached on each of the parcels that are being delivered. What the red tag does is that it figures out where, when, and what part of the parcel is being damaged, and from this we can infer if the damage is small or in huge amount, and this in turn goes as a review or a feedback to the officials who are handling this, and can actually predict what and when the damage has occurred. So extra care can be taken, and the efforts put in taking care of the smaller parcels can be reduced. This is another simple application. Information and the applications have been inferred from. These are the various papers we referred through. And with this, we would like to end our presentation. Thank you.